Alright, so finally we get back to chapters where we're actually going to do some math. Yay! You'll actually need your calculators here today for one of the activities that we'll be doing. But basically in chapter 5, we're going to start to take a look at the concept of probability and how to calculate those out. So, we just first start off with the definition of probability, and when we talk about probability, we're talking about a proportion. Basically, a proportion of the times that a certain outcome occurs as it says here, in a series of a very long set of repetitions. Right? So it's like flipping a coin thousands upon thousands of times. If it's a fair coin, what's the probability of it being a heads? Really? We don't know what the probability of getting... 50. Okay, 50% or 0.5. Okay? But it's like in a long series. Okay? And that's the important piece. When we talk about probability and we talk about the outcomes, our answers for probabilities are always answers between 0 and 1. So that, to me, that's a huge important piece. So when we're calculating probabilities and we're adding them together and doing all sorts of things with them, our answers, though, if we're still talking about a probability, need to be between 0 and 1. Okay? I've had, experience of students give me answers telling me the probability of something is 1.3. That would mean 130%. And that's not possible. There's only 100% of possibilities out there. So, one of the concepts that we'll talk about here today is this law of large numbers. Okay? Meaning this. When you observe more and more outcomes or more and more repetitions of some sort of probability event, okay, that probability will get closer and closer and closer to a single value. And a lot of times it gets closer to what we call the theoretical probability. Okay? So to demonstrate this concept of the law of large numbers, we have actually two graphs here that demonstrate this, okay, of what we call maybe short-term versus long-term. So here it describes, up top it says, if you flip a fair coin, you'd expect the portion of getting heads to be 0.5. But in the first graph, it will show the proportion of heads for the first 20 coin tosses, and then in the second graph, the proportion of heads in the first 500 coin tosses. So this first graph really is kind of showing you what we would call the short run behavior versus the long run behavior. And in probabilities, what we're really focused on is the long run behavior. Okay? So if you look at how this graph is read, okay, these are the number of times you've tossed the coin and the set proportion of heads. So on the first coin toss, your proportion was actually 0, which basically meant you got a tails, because 0 out of 1 were heads. So on the second coin toss, you actually got a heads because we actually had 1 now out of 2. Well, since it went down, this would be 1 out of 3, 1 out of 4, 1 out of 5. Since it's going up, 2 out of 6, 3 out of 7, 2 out of 7, 3 out of 8, 4 out of 9, 5 out of 10. And so what it's doing is it's graphing these proportions. So if we were to actually divide these out, we'd be at 0.5, 0.33, 0.25, 0.2, 0.33, and so forth. And what we'll see is in the first 20 coin tosses, some of the time we're not even close to the actual proportion of what we think it's going to be, 0.5. Okay? However, when we start to look at the long run here, which is just a continuation a little bit of this particular graph here, you can see we fluctuate, from basically 0 up, and then we're below it, but then all of a sudden we go above it, below it, and then it starts to get really, really close, even though there will be times where it doesn't equal exactly 0.5, but in the long run, it's really, really close to that value, and many times in the long run, at that value. So the important thing about understanding probability is that we're really looking at this law of large numbers, or basically law of large outcomes. Okay? We're looking at doing the flipping the coin, or rolling the die, or doing the experiment many, 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 many times. Okay? So, in our example, to start us off here, it says, according to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. So in part A, it asks us to explain what does 0.61 mean in this setting. Okay? So when we're ever given a probability, we're talking about if we're actually given like a large sample. So what does this 0.61 mean? Well, if given a large sample of U.S. adults, we would expect about 61% of them to eat breakfast. Yes.
I have the other two.
Oh, yeah, awesome. Alright. So in B it says, why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them usually eat breakfast? Well, we would say something to the extent of this: since this is a sample of just 100 adults, we know that if we repeated the sample, we could have more or less than 61 say yes. The key part here is we can't say the word exactly, because we know variability can occur from sample to sample. I might even just note that. Variability can occur from sample to sample.
Oh my God.
Because if it was exact, if we each went out and surveyed 100 U.S. adults, we all should get 61. But we know that that may not be the case. All right, number 2 says the probability is a measure of how likely outcomes are to occur. It says match one of the probabilities that follow with each statement. Be prepared to defend your answer. So an A says the outcome is impossible. It can never occur. Okay, that would be 0. Why?
It can never happen.
Okay, the key word is impossible, so no outcomes will ever happen. Hence, it is 0. All right, B. This outcome is certain. It will occur on every single trial. 1. Okay. It always happens. Hence, it is 1. Switch colors here again. All right, C. This outcome is very unlikely, but it will occur once in a while in a long sequence of trials. Okay? So, the question is, if you were to at least narrow it down to 2 choices, which 2 choices would you choose? Okay? You'd probably look at either 0.01 or 0.3. But what's going to make you pick one versus the other? Okay, it occurs once in a while in a long sequence of trials. 0.3 is like saying 3 out of 10 versus 1 out of 100. So which one seems to be a long sequence of trials? 0.01. So 0.01 is the better choice due to the long sequence of trials. And the last one, D here, says this outcome will occur more often than not. So is it 0.6 or 0.99? So 0.6 would be 6 over 10 versus 99 out of 100. When we're saying more often than not, that kind of refers to almost like saying just more than. Would you agree that that's kind of like saying more than half? Okay, so which one's closer to more than half?
0.6.
0.6. So 0.6 is a better choice since it is more than 1/2, but closer to it. You could also say that, well, plus 99, it would be almost like saying almost certain. You know, there's that one chance that it might not happen. All right, any questions so far with the concept of probability? And today is really focusing around this concept of probability. All right, let's flip to the second page. And we're going to talk about a couple myths that come up about randomness or just around this concept of probability. Okay? First of all, the first myth here is called short run regularity. Okay? Basically, it's the idea that probability is that randomness is not only predictable in the long run, but it's also predictable in the short run. Okay? What happens is many people feel that probability should especially when you're doing certain things, if things haven't come up, that they should come up right away the next time. Or if something is equally likely to happen, if I got one outcome previously, I should be getting the other outcome on the next draw. And that's not necessarily the case. So for us to demonstrate this and to see this outcome or this myth in action, have this kind of step-by-step activity that we're going to do here together. So it's very important that you use your imaginations here today. Okay? So, first thing you're going to do is you're going to pretend to flip a fair coin. So, imagine that you got a coin in your hand. You put it on your thumb. You flip it up in the air. You catch it. You put it on your hand and you look at it. Okay? What do you see? Okay? Write down what you see. Did you see a heads or a tails? Use the letter H for heads. Use the letter T for tails. So I want you to actually imagine flipping it, boom, catching it, looking at it. What do you see? That's what I saw. Just out of curiosity, how many of you wrote down an H? Okay. How many of you wrote down a tail? How many of you didn't do it? Okay. Yeah. So now, imagine a second coin flip. So imagine having that coin in your hand. Toss it up in the air, catch it, flip it, look at it again. Okay, what do you get? Write that result here. Alright, everybody got there too? Alright. Now, you're going to keep doing this for 50 imaginary flips. Okay? So, and you're going to write down your results below. Okay? Put them in groups of 5 to make them easier. So, like I started with tails, heads. Okay? So, if I go tails, then heads. If I do it 5 more times, say it came up tails, tails, heads. That would be my first 5 coin flips. I'm going to do this set of 5 9 more times to get 50 coin flips.
Right? So you just use the same sequence.
You don't use the exact same sequence.
Oh, okay.
You're actually imagining what would be coming up next. What would be coming up next. Okay? So you're going to do another set of 5, but it might be like heads, heads, tails, tails, heads. Or it might be tails, heads, 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 and so forth. Okay? So right now, I'm going to give you about a minute or 2 to do this. Shouldn't take you very long to imagine flipping the coin each and every time. But this is very important to do because you're going to need these results for the next part. Okay? So don't wait for me to do it. I want you to have your own separate results of 50. Because if you don't do it yourself and you just use my answer, then my answer is going to cause a little bit of bias. You can't have that bias, that would be bad. Anyone still need about 30 seconds or so to finish up your 50 imaginary coin tosses? All right. So now what we're going to do is we're going to look at your results and look at how many runs of each length are in there. Okay? Now you might be going, what in the world is a run? Okay? So right here in number 4 it says a run is a repetition of the same result. Okay? So in the example in part 3, in my example up here, notice how it went heads, tails, heads, tails, heads, tails, tails. This 2 tails in a row would be a run of 2. Okay? Likewise, the next heads, heads together would be another run of 2. What we want to look at here is how many runs of 2, how many runs of 3, how many runs of 4, 5, 6, 7, 8, and so forth are there. So, if I start to take a look, what I like to do is look at how many repeat and how long is it. So I have a run of 2 there, a run of 3, a run of 2. Heads, tails, heads, tails, heads, heads. There's a run of 2. There's a run of 2. Heads, tails, heads. Ooh, run of 3. Tails, heads, tails, heads. So that did repeat. Ooh, there's a run of 4. A run of 3. Okay. A run of 3. Another run of 3 and a run of 2. So what I want you to do is in your list right now, some of you are following along and actually doing your list. I want you to do the exact same thing as I did here, is to start to group and look at how many runs of 2 and how many runs of 3, how many runs of 4 or 5 or 6 or 7, even a run of 8. If you have even a run longer than 8, just note it. Like if you have something out here like a run of 12, then just tell me that you had a run of 12. Once you have counted or noted how all the different runs, count how many runs of length 2 and 3 and 4 you have. 5, 6, 7, 8 also. So here's a run of 2, 1, 2, 3, 4. I had 5 runs of 2. I had a run of 3, that's 2, 3, 4, 5. Oops, I missed a run of right here, so I actually had 6 runs of 2. And I had 1 run of 4, but I have no runs of 5, 6, 7, and 8. I'm going to give you a minute or so to do that. So you had 10, 2, 1, okay. Oh, you had 1 run of 6, nice. Oh, how many runs of 2? 12. Wow, bro. So 9 runs of 2. That was it. Wow. Thank you. 9 and 1. Okay. Starting to see kind of just in the process of counting them up. 1 run of 6. That's good. Ooh, 2 runs of 5. Nice. So you had a streak. You had a little streak in that. Okay. 2 runs of 5. 4 runs of 5, huh? Okay. Yeah, no, run of 50, thank you. That was insane. 91, okay. Yeah, 5 11s. Ooh, you had a 7. Okay. You made up of a run of 7, okay. Next run's a 2, okay. That would be a run of 4. Yeah, that would be counted as a run of 4. Yeah. Yeah. It's back up for a minute. But if it gets loud, I'll have to keep having to do that. Alright, so now, the reason why we do this is not everybody, but just just going around the room, okay? A lot of people had a large number of runs of 2. That tends to be common, okay? Meaning they might have 5, 6, 8, 10, even 12 runs of 2. Then the number of runs of 3 tend to decrease a little bit. Some of you had similar numbers, okay? And then when we got to the runs of 4s, 5s, 6s, 7s, and 8, they start to decrease. There were a few of you. I think there was one person that had 5 runs of 5, okay? There was a person who had a run of 7, and we even had one person who had a run of 50, okay? They imagined that coin came up tails every single time. Nice imagination, okay? Now here's the thing. Most of you had a distribution that looked like this, okay? 2, 3, 4, didn't see a 5, 6, 7, a run of 8, a 9, a run of 10, or so forth. The reason that happens is because you're thinking it's a fair coin, so you're thinking it has to alternate heads, tails quite often. But here's the thing. If you actually start to do a decent amount of coin flips, we're only going to do 50, so there's a little bit of risk here. You'll actually start to see a string of 5, 6, 7, 8, 10, 12 heads or tails in a row, okay? So to demonstrate this, we're not going to use table D. I'll spare you that. And we're going to use our technology. And I'm going to show you how to do this on your technology pretty quickly, okay? So take out your calculators, okay? It will be interesting because depending on if your calculator's been reset or not, some of us might get the exact same results. Mine might be different than yours because I'm going to be at a different spot in the random number table, okay? Because I do this quite a bit with my calculator and I don't reset it. So, I know I had my calculator on earlier, but it must have shut off. So my calculator is going to take a minute here to load, and we'll show you how you can simulate flipping a coin. Now I know some of you have the updated versions on your calculator and actually have a coin simulator on your calculator. But I'll tell you right now, it'll take you 5 times longer if you use that app instead of doing what we're going to do here right now. So what I'm going to do is I'm going to actually simulate flipping a coin. How many outcomes are possible? 2. So what I can do is on our calculator, if you go under your math menu should be in the left column about the 4th button down. You go to this math menu and you'll see in the upper right corner PRB, which stands for probability. So I'm going to use my right arrow and highlight probability. Okay. What I'm going to choose is where it says random integer. It's number 5 for me, but depending on your calculators, it could be a different number. But I want to choose this function, random integer. What it does is it's basically going to use your random number table and it's going to pick integers for you. Integers are positive and negative whole numbers. So what I have to do with the calculator is tell the calculator, I need to tell what the interval is. So I'm going to go 1, 2. I'm going to choose the numbers 1 to 2. Meaning, the outcomes the calculator is going to kick out here are just 1s and 2s. 1s are going to represent heads, 2s are going to represent tails. And then what I can do is tell the calculator how many times I want to do it. How many times do I want to flip this coin? 50 times. So I'm going to close the parentheses. Yeah?
What was the comma again?
It's right above the 7, I believe. So I can go ahead and hit enter, and it will give me this string of 1s and 2s. Now, I know for some people this is hard to see, okay? So this is what I like to tell students to do. You have, right above this on key, this STO with an arrow button. This allows you to store your answer somewhere. So we're going to take the previous answer and store it somewhere. So this STO key that I just hit, which is right above the on, it's going to take this answer, this string of numbers, and I'm going to simply put it in list 1. So I'm going to go the store key, second 1. So again, the store key, and then second 1. I'm going to hit enter. It's going to just repeat the numbers for me. But here's what's nice about it, is once I've done this, if I just go to stat and edit, look at my list 1. I got some other stuff here. I'll just clear this out. But now it's puts the numbers nice in order for me. So what I can now start to look at is how many runs of everything do I have here. Okay. So I have a run of 2 because I had 2 2s. Then it alternated here. Here I have a 1 1. Look at that. At a run of 4 right away. 2 1 1. There's a run of, there's a run of 5, right? Or no, I'm sorry, that's a run of 4. So there's a run of 2. Another run of 4. Wow. Run of 2, a run of, another run of 4. Wow. Okay. This is interesting. A run of 3. Wish I was noting these right ahead. Here's a run of 4 again. Okay. A run of 2, a run of 3. A run of 3. Almost at the end here. A run of 2. A run of 2. I got to the end. So in my sample here, I think I had like 4 or 5 runs of 4. It was actually probably the most common occurrence that actually happened. Okay? But I did get a run of 7 or 8 or 9 or 10. Okay? How many of you did this random integer piece on your calculator? Okay, a few of you. Take a look at your list right now and let me know if you got, I want to see what your longest run actually is. Okay, did you store it yet?
No.
So here's your store key. So what you want to do is hit that bottom key, store. So go ANS and then second 1. Second function and 1 so that you can put it into your list. Okay? I'm sorry, I heard someone say they had a run of what?
8.
Had a run of 8? Run of 8? Did anyone else have a run of 8? Okay, we had 3 people with a run of 8. Okay? My guess is you might have been at the exact same spot. Anyone have a run longer than that? Okay? So what this drives at here is it drives at this myth of the regularity. You want to switch answers quite often, okay? When you're trying to imagine flipping a coin because it's, it's fair. So heads and tails should almost be alternating. Okay? No one actually did that in their imagination when I looked through the list. No one had no runs of anything. So I usually get one person to do that and one person to give me like all heads or all tails. Okay? So I don't know my exact numbers here, but I want to say I had about 4 or 5 here. I only had like 1 or 2 here, but I had like 5 runs of 4, but I didn't have anything bigger than that. But there were 3 students in this class.
No, just one. There's only one person. Just she was saying it was.
Oh, it was just you? I thought Iola raised her hand and said that she had 3. Or I'm sorry, you had 8, right? Okay, so all right, I'll stand corrected. 2 students that had a run of 8. Okay, so what we're trying to drive at here is it says compare the 2 results. Which table had the longest run? Okay, the random table will have the longest run. If you were to actually do this, say, for 1,000 coin flips, I can almost guarantee you that you will see a run length of at least 8, if not 9, 10, 11, or 12 in it. Okay? I used to have a professor at St. Olaf College that he used to give as assignments. He didn't do it for our class, but he used to. First day of class, he would say, here's your homework assignment tonight. I want you to go home, take out a couple sheets of paper, flip a coin 1,000 times, and record the results. Bring them back to me. And he could just look at the papers and see whether or not the student actually did flip the coin or actually made up the data. And how he would base it on is he would look for those runs. If they made it up, they would not have a run basically longer than 4 or 5 heads or tails in a row. But if you flip a coin 1,000 times, you're going to have runs of 7 and 8 and 10 and 12 in a row. Just to show you, here on the calculator here, if I do this real quick, if I go if I go back to my math, go to probability, and I'm going to go back to this random integer. Whoops, I'm sorry, I was still in the list mode, so I'm going to clear this out here and start from the beginning. If I go to math, probability, random integer, 1, 2, and I'm going to do it instead of 50 times. Let's look at a string of, say, he did 1,000, but for time's sake, I'm not going to look at 1,000 numbers. Let's just look at 250 and see if we get a nice long run here. So we're starting off here, this is what's fun, is we're looking for when we get a long string. We got a string of 4 there. String of 3. Now watch, this will be the one time it doesn't happen for me. String of 4. Ooh, look at that. How many 2 so far? 6, 7, 8. So we just had a string of 8 right there. Ooh, look at our 1s now. 2, 4, 6, 7. That's 7 of them. 8, 9, 10, 11. Just had a string of 11. Okay? I know I get excited about this. Okay? So we had a string of 9 and a string of 11 already. You want me to go to the very end?
Yeah.
Or can I stop?
Keep
Ooh, 2, 4, 6, 7, 8. Oh, so we had a 7, an 8, and an 11. Thank goodness I only did 250. Ooh. We'd be here for a long time. How many have I done so far? That is a good question. I don't know for sure. We're still haven't. So 8, what do we have? 8, 9, and 11? Nice. Poor person who's watching this video because they missed the notes. This is where you fast forward, right? Thank goodness you can do that. Ooh, here we go. We're gonna, oh, that was only 5. That was bummer. Ooh. Oh, they're kind of glitchy here once in a while. Ooh, here we go. Oh. Look at my hands getting tired. I'm still going. You said to go to the end. I gotta be at least in the 150, 200 range right now. Ooh, here we go. 2, 4, 6, 7. Oh. Oh! That's another, I think, 7. But even in 250 right now, we've had what? 2 or 3 7s, an 8, a 9, and an 11. So what happens is many times, because of that myth, students believe that the 1s and 2s should alternate and not repeat very often. But in reality, they will. Oh, I got to the end. Phew! Oh, thank goodness, because this arm was getting tired now too. Okay? But you can start to see that the length of the repetition, okay, does actually get very long. Okay? Alright, so now, okay, our second myth, okay, is this myth of the law of averages. Thank you. I got to grade it yet. So the myth of the law of averages basically says is that when a long streak of a certain outcome occurs, future outcomes must balance it out. That is not truly the case. Okay? So what happens here is like in this example, it says if I flipped a fair coin 6 times and got tails, 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 tails. 6 tails in a row. What's the probability that the next coin toss is a heads? It's still 50-50. It's still 1/2. Okay? But guess what many people will believe? Okay? They'll believe that the probability that the next one's going to be heads, okay, is actually greater because I've had 6 tails in a row. But what has happened in the past doesn't impact what's going to happen in the future. Coin tosses from one coin toss to the other is independent. The probability doesn't change, and we're going to talk about that definition. Okay? So, and that's what we're talking about here. Okay? It has no memory. Any of you familiar with the casino game roulette? Okay. So if you're not, I'll try to help those that aren't familiar with roulette. But roulette is this big spinning wheel that, depending on the roulette wheel, will either have 37 or 38 numbers on it. 18 of them are colored black, 18 of them are colored red, and either 1 or 2 are green depending on the wheel. Hence why you get 37 or 38. Okay? So what happens is at certain casinos, okay, one of the bets you can actually make at a casino is the color of the next roll, red or black. And they pay you basically equal odds. So if you bet $5 and it comes up your number, you get $5. Now the odds are in the casino's hand because it's 18 out of 37, which is not quite 50%. Okay, that's how the casino's making money. But what else they do at a casino is they will actually put up the last 6 to 8, or usually like the last 20 rolls on a roulette wheel. They'll give you that information because they know it doesn't impact the next roll. But what happens is someone might see on the wheel, instead of tail, 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 they'll see, oh, the last 6 rolls were red. I'm putting all my money on black. Because, hey, you can't have 7 in a row that come up red, thinking the probability's in their favor. But it actually is not. It's still the same probability. It doesn't remember what occurred on the last roll. They don't impact each other. And that's the second myth. Okay. All right. Go to the last page because the notes did spill over just a tiny bit today. Because I couldn't squeeze all these concepts all on one page. But the last concept basically gets to this piece of independent outcomes. It's basically where past events do not change the probability of future events. Okay? So flipping a coin, okay, though flipping a coin and noting heads and tails, Those are independent events. The outcome does not influence the other. Rolling a die. If I roll a 6, okay, 3 times in a row, the probability, okay, that I roll a 6 again still remains 1 out of 6. Even though some people might think, I'm not going to roll a 6. You can't roll that many 6s in a row. Okay? But the probability stays the same. However, there are outcomes where you do things where the probabilities do change. And if they do change, then the events are not independent. So independence becomes very important in probability. So to give you an example here, it says there are 12 girls and 13 boys in a class. The teacher places the student's name in a hat and draws out 2 names. What's the probability that the first name is a girl? Okay. So when I look at probability and there's outcomes like this, I sometimes will note first name is a girl. So how many names are girls? 12. How many total names are there? 25. Okay? So the probability that the first name is a girl is 12 out of 25. If you put that as a decimal, you don't have to, but if you did, 0.48. Okay? So now, what's the probability that the second name is a girl? Is it still 12 out of 25? Well, oh, one of the names has already been drawn, right? So, how many girls are left? How many names are left?
24.
24. Okay. So the second name being a girl is now just 11 out of 24. So are they independent events? In order for them to be independent, they would have to be the same probability. So no, they are not, because the probabilities change. One less girl and one less student. We'll put that in parentheses. Meaning, one less girl on the top and one less student on the bottom. So what can happen sometimes when we take a look at probabilities and certain outcomes and events, in this particular case, when you actually draw 2 names out at once, you're not actually putting that first name back into the hat to get chosen again. So sometimes we call this what we call sampling without replacement. When you don't put the names back in, okay, it changes your probabilities. Now, if I took one name out at a time, noted it and put it back in, did it again and noted if it was a boy or a girl, then the events would have been independent. Okay? But there are many things, okay, that we look at where independence doesn't happen. Okay? Probably the most common thing that deals with probabilities in society is cards. Okay? You go out to a casino and play blackjack. Okay? Roulette, okay, is a game where the probability of one outcome versus the other doesn't impact the results. Meaning the spin of one wheel doesn't impact the spin of the next wheel. However, in the game of blackjack, okay, since the cards aren't reshuffled during every single hand that you play with the dealer, okay, every card that is exposed that you see changes the probability of what the next card will be. Okay? Because in, like, for instance, in a deck of cards, just one deck, there's 4 aces. Right? If the first card you're dealt in blackjack is a 10, okay, and that's the only card you've seen, okay, normally you would say the probability of getting an ace is 4 out of 52 or 1 out of 13. But if the dealer deals you a 10 card, whether that's a jack, queen, king, or a 10, okay, the probability that your next card is going to be an ace is not 4 out of 52, but 4 out of 51, because you know the outcome of one of the cards. If you know the dealer doesn't have an ace, then you know it's actually 4 out of 50, which actually increases your chance of getting that ace. So that's why if you've ever saw the movie 21 and they count cards, okay, they're doing that on purpose because they're figuring out basically the probabilities of better hands of getting blackjacks or getting high hands or hands where the dealer will likely break, putting the odds of blackjack actually in the long run in their favor. All right.
Mr. Morris,
Yes.
do you know how to count cards?
Do I know how to count